So then, good morning, everybody. Once again, I act for Professor Knapner since, at least for today, he wanted to preserve his voice. So, on Tuesday, Professor Knapner introduced the so-called gradient method, which is an iterative method to determine approximations for a linear system where the matrix A is symmetric and positive definite. And the idea is to minimize this. Unfortunately, I have no pointer for today, but I think it should also work. The idea is to minimize this functional f, which is equivalent to solve this linear system ax equals to b. And the idea is to find a direction. In the gradient method, it's the minus of the gradient. So the idea is to get the minima in one direction, that is the direction of the steepest descent. And the iterative, in the case of the gradient method, is the iterate xk plus 1 equals to xk plus any scalar number times the search direction xk. And in the case of the gradient method, this scalar alpha k was defined as dk transpose times dk divided by the energy scalar product of dk, that's the search direction of itself. So, well, and we also have seen that the convergence rate here is not that good. It's quite similar to the Jacobi method. And that the reason is, or one reason is that these different search directions do not be orthogonal in complete. That means that, for example, such, as you see here at this figure, such zigzag phenomena can appear. And to avoid that, we come to so-called conjugate methods. What does that mean? Well, we define as follows. Vectors from d0 to dl are called conjugate in the case that they are in some sense orthogonal to the with respect to the energy scalar product that is defined here below. And that means if we are defined these searching directions, in that case that they are conjugate, our method or iterative method is called conjugate method. And one very nice property of these conjugate methods is that they lead to the exact analytical solution in the case of we at least apply m steps. And m is the dimension of the space. Well, I want to prove that. Today it's a quite extraordinary lecture in that sense that the most of this lecture will take place at the blackboard. That's the reason is we only have 4 slides for the topic for today. So please let me know when you can't read what I'm writing here. So I want to call it lemma 5.2.1 because it's the chapter 5.2. So for a given initial vector in Rm, we consider the iterates, and the iterates are defined Similarly, then here for the gradient method, that is nothing but the kth iterate plus the scalar alpha k times the search direction. And with alpha k is defined as minus. And now it's more or less like this alpha k, but a little bit different. Gk, and Gk is the gradient of our functional f, that is nothing but the residuum of our linear system. So it's the matrix A, I write it down here. Gk is nothing but axk minus b. Okay, this is the gradient at point xk of our functional f. Gk transpose dk divided by dk transpose a dk. Okay, this is alpha k, and okay, and gk is defined here as follows. And this is nothing but the gradient of x at point xk. And conjugate directions d0 up to dm minus 1. So at the moment, this is a very general iterative method with the only really required assumption that these searching directions are conjugate in this sense I already mentioned. In that case, a method of conjugate directions is exact after at most m steps. Yeah, and m is nothing but here the dimension of our space. That means that the mth iterate is nothing but the exact solution. I denote it here by x star. So x star is the exact analytical solution. Well, that's a very nice property, but in fact it's a very useful theoretical property. So in practice you have, for example, due to the finite element method, you have very big linear systems with several hundred thousands or millions variables. So you do not iterate 100,000 times or million times. Do not apply this iterate method. So, you terminate your iterative method earlier and take your iterate as an approximation of this exact solution as usual. But at least for the theory, it's a very nice result. So how we can prove it? Of course, since our conjugate directions, well, they are conjugate, and in particular, that means they are linearly independent, and we have m linear independent vectors. That means that our conjugate directions span the complete space Rm. So, for example, we can represent x star minus the initial vector x0 by a linear combination of the direction, these conjugate directions. That means that Applying now on this vector this matrix, and then apply again this ith conjugate direction. This is nothing but alpha I di transpose a di due to the conjugateness somehow, since di transpose a dj, when j differs to I, is 0. This holds, and that means that alpha I is nothing but di transpose a x star minus x0, and due to the positive since A is positive definite, this guy here is greater than 0, so we can divide by it. Okay. And Ax star is nothing but B, so we can rewrite this as follows. This is nothing but Ax0 minus B divided by this guy. Okay? So, well, the only thing we have to show is that what still remains is that this term here, or not only this term, but this alpha I coincide with these alphas, with these scalars. Yeah? And then you see that we can, due to the fact that here our iterate can also be rewritten as this is the initial vector plus the sum of alpha j dj from j equals to 0 to k. Okay? And so in the case that k equals to m, indeed our iterate xm equals to x star. Okay? So what remains to show is that Gi transpose Di, this equality. But Gi transpose Di is nothing but, due to the definition of Gi, Xi minus B. Okay? This is only the definition of Gi. And but there holds Di transpose A Xi, and that is this guy here. So we have now to show that Di transpose A Xi, that means Di in the energy scalar product with Xi is the same than Di and Xi in this energy scalar product. Okay, but this here is nothing. Now I rewrite the ith iterate Xi as follows. This is nothing but the initial data plus the sum alpha j dj from j equals to 0 to I minus 1. Okay? But due to the fact that the directions are conjugate, this is indeed nothing but the first term. Yeah? Since the sum here is a sum up to I minus 1, so every summand here is 0 with respect to the energy scalar product with this guy Di. Okay, so we see that indeed conjugate methods leads to an exact solution in the case of we have enough iterations. Further, the next result is that these conjugate methods indeed minimizing our functional f on such a subspace that is given here. This is an affine subspace. We have the initial data plus such a span of the conjugate directions. And moreover, we have some orthogonality of our gradient at the point xk, at the point of the kth iterate, and all conjugate directions we have applied before. Okay. This should be the next lemma. I call it 5.2.2. So the vector xk defined in lemma 5.2.1 minimize. So this is nothing but the kth iterate of our conjugate method. Minimize the functional fx 1/2 x transpose ax minus b transpose x on this affine subspace. And why this subspace, the span of the conjugate directions, is called k with a subscript with k with the arguments a and g0, we will understand in the next theorem, in the next result. And this is due to the following. This is the orthogonality of the gradient and the search directions for I up to k minus 1. And this orthogonality I will call star. Okay. The first step, step 1, is to show this property. And how we do that? Also, this first step we divide in 2 steps. The first step is to show this property in the case that I equals to k minus 1. So it's the previous conjugate direction of our iterative step. GK. Is it readable for everybody? Yeah. Also in the back, can you read it? So, GK is nothing but, it's the gradient of our functional, so it's A, the matrix A times applied on our k iterate, xk minus b, and xk is nothing but here. It's xk minus 1 minus alpha k times the conjugate derivative dk minus 1, and alpha k minus 1 is this guy here. So altogether, this is A times xk minus 1, k minus gk minus 1 transpose dk minus 1 divided by dk minus 1 transpose A dk minus 1 times dk minus 1 minus b. Okay, so maybe I use some color. So this bracket and this bracket belong together. Okay, but now we see that, now what do we see? Well, this is nothing but d k minus 1 t a x k minus 1, okay, this is the first guy here, minus g k minus 1 transpose d k minus 1. This is due to the fact that here the dk minus 1 transpose a dk minus 1 cancels with dk minus 1 transpose a dk minus 1. So this is left minus dk minus 1 transpose minus times minus b. So it's, yeah, the minus is already here. Okay, but this, due to the definition of gk minus 1, is 0. Yeah? Gk minus 1 is the gradient of the functional. It's nothing but ax k minus 1 minus b. So indeed, this is 0 by definition of our gradient gk minus 1. So the next step is to show now this result, this orthogonality for components I that are less than k minus 1. And for this, we are looking at dj minus L minus 1 transpose gk minus gk minus L. And of course, due to the first step, small I here, this product, this conjugate direction times this second guy here, gk minus L, vanishes since they are orthogonal due to this result here. So this is indeed nothing but the product of this conjugate direction and this gradient gk. But due to the fact that this here is nothing but a times xk minus xk minus 1, also by definition of our gradients, minus b plus b, we can rewrite this is nothing but the conjugate direction dk minus L minus 1 transpose times the sum from j equals to 1 up to L of alpha k minus j a d k minus j. Okay, so we only also again introduced or used the definition of our iterate, kth iterate and k minus L iterate. So this here. This is nothing but the initial data plus such a sum of a linear combination of our conjugate directions. But since the directions are conjugate, and we have here a product of such conjugate directions, indeed, this is 0 as well. Okay, what's still left is the minimizing property of our kth, this kth iterate. That means that it's indeed the minima for this functional on that affine subspace. So, to see that, we assume that this vector D is some arbitrary vector belonging to this subspace, which is spanned by our conjugate directions D0 to dk minus 1. Then dt gk equals to 0. This is because of this property here. Yeah, D belongs to the span of all conjugate directions, and our gradient is orthogonal to these conjugate directions. And therefore, we have that our functional at point the k iterate plus this arbitrary vector D. This is nothing by the definition of the functional than 1/2 xk transpose a xk plus 2d transpose a xk. This is due to the fact that A is a symmetric matrix, plus d transpose a d minus b transpose xk minus b transpose d. Well, but this is nothing as xk d xk plus dt a d plus, well, here we have 2 and 1/2, that cancels out, so there is nothing but dt axk minus dtb. So here, of course, the standard scalar product is symmetric, so we can here change the b and t. And this is, here we have axk minus b. This is nothing but the gradient gk is 0. This is 0 due to here our result before. And what left is this guy, btxk. Well, but this is nothing as our functional at point xk, the kth iterate, plus 1/2 dtad. Okay? But since A is positive definite, this is greater or equal to 0. So we see indeed that the kth iterate minimizes our functional on this affine subspace. Okay, are there some questions? Okay, so we have seen that an arbitrary conjugate method is exact for if we apply enough iterative steps, and indeed it minimizes our functional. So in certain subspaces, affine subspaces. But now the question is, how do we choose such conjugate directions here? We are assumed to have already chosen, in some fact, to have such a conjugate method. Well, this gradient method you have learned the last Tuesday is not that bad. So the directions we choose here will be quite similar. The direction of the steepest descent here, dk plus 1, is again something like minus the gradient of the k plus 1 plus some correction term. And this correction term, beta k, plus this conjugate direction dk, is to indeed to ensure that the search directions are conjugate, as you see here above. So at least what you see above here is the assumption that our conjugate, our search direction dk plus 1 and the previous search direction dk, these both should be conjugate, then this is equivalent to the fact that this correction scalar term beta k has, looks like it is written here. It's the gradient G transpose AD divided by dAd. So, and if we define now our searching directions, as we have done here, and this correction scalar terms beta k, as it is written here, then the method is called the method of conjugate gradients. Of course, it's the combination of our gradient method and the conjugate method. Or abbreviative, it's called the CG method. And this method especially has quite nice properties. What's still missing here is that the first direction, d0, is indeed the minus the gradient. So indeed, for the first step, we follow the direction of steepest descent. So maybe I write it down here. d0 is indeed defined as minus the gradient g0. So this definition is still missing here above. So one of the nice properties you can see here on the slide, but I also write it down once again at the blackboard, is that these strange subspaces K, A, G0, which were spanned by our conjugate directions, indeed now is also spanned by the gradients G, or it's spanned by the gradient of our functional at the initial data, g0, and this vector is applied several times. At this vector is several times applied the matrix A. So it's spanned by these vectors g0, hg0, a squared g0 up to a with exponent k minus 1 g0. So with this in mind, now this denotion of the subspace with argument A and G0 makes sense. So now let our gradient for the k minus 1 step is unequal to 0. Then the following assertions hold. As they are, the first is then also the conjugate direction is unequal to 0. And our subspace K indexed with K with arguments of the matrix A and G0 which is defined as the span of D0 up to dk minus 1 is the same as the span of G0 up to gk minus 1, and this is the same as G0, A, G0 up to A with exponent k minus 1, G0. Okay? And this space or subspace is called the Krylov subspace of dimension Well, the dimension of this space is indeed k. That's why it is indexed with k, of dimension k. And of this matrix A, with respect to the direction, the gradient at the initial data G0. So I think next Tuesday, Professor Knappner will introduce several Krylov iterative methods in Krylov spaces. So, but this CG method is one of so-called Krylov subspace methods. But this only works in the case that A is indeed a symmetric and positive definite matrix. But Krylov subspace methods are more general than only this CG method. The next property is that for all components I and j, indeed, our directions we have now determined or defined here above are indeed conjugate. This is by the choice here of beta k is not that clear. A priori, we only see that the conjugate direction and the previous conjugate direction are conjugate, but indeed all conjugate directions, all directions we have defined above are conjugate. And finally, to reduce the computational effort, it's not necessary indeed to always here multiply a vector with a matrix and this vector again. So we can reduce it by a vector-vector multiplication. Since alpha k, this scalar is nothing but the scalar product of our gradients k divided by this guy. So we see okay, this is the same, more or less, of the computational effort, but at least here we can reduce our effort since we do not need here this matrix A in between the vectors. Okay. So, let's prove also these assertions. The first three assertions here we prove by induction with respect to k. And for the case that k equals to 1, okay, it's quite trivial since d of 0 is nothing but minus g0, and g0 is not equal to 0. That means that minus g0, of course, not equal to 0. Here, this Krylov subspace of dimension 1 is nothing but d0. This is minus g0, so it's the same span than here and here. Okay. And here, we only have, in the case that k equals to 1, two different conjugate directions, that is d1 and d0. And of course, due to the choice of beta k, we see here above that these are conjugate, these both vectors. So more interesting is the case, induction step. So we assume that gk does not equal to 0. Then the exact solution, this is nothing but the inverse of A applied on B, does not belong on x0 plus this Krylov subspace. Otherwise, the CG method would terminate. We have already at the k minus 1 iterate would be the exact solution, and the gradient is 0 at this point. So since dg is defined as minus gk plus beta k minus 1 dk minus 1, we have that the span of g0 to gk equals to the span of d0 dk. Okay? By assumption, we know that the span from g0 to gk minus 1 equals to the span of d0 to dk minus 1, and now dk is nothing but a linear combination somehow of gk, of this vector, plus a vector of the previous span, so the spans equal. So the identity gk equals to gk minus 1 plus a xk minus xk minus 1. This we already have seen here above. Above the word minimizing property, you see that the different of the gradients is the different of the iterates applied with the matrix A. But this is nothing than gk minus 1 plus alpha k minus 1 a dk minus 1. Okay, this is due to the definition of the kth iterate. The kth iterate is the k minus 1 iterate plus this guy here. And this implies that this vector gk indeed belongs to the span g0, a g0. So we assumed that, one moment, a k minus 1 g0, a k g0. Okay, we assumed that gk minus 1 belongs to this, to the span of these vectors by induction, and then gk, since we once again apply here the matrix A, also dk minus 1 by definition of dk minus 1 belongs to the span of these vectors. Then we once again apply the matrix A, so we have to extend the span in that case. Okay? So that means that our subspace K is at least contained in the span of these vectors here. Okay, so it left to show that these vectors, or the span of these vectors, is contained here in this subspace. Or, which is equivalent somehow, is that we show that the dimension of this subspace is k, or k plus 1. So on the other hand, d0 up to dk minus 1 are by assumption linearly independent. And for all I less than k, we have di transpose gk equals to 0. That is why? Well, that is because of lemma 5.2.2, here this equation was marked with star. This is because of this star. But that means that also d0 up to dk minus 1 and gk is linearly independent. Okay? But we already have seen that the span from d0 to dk minus 1 is the same than the span of g0 to gk minus 1. So that means that the system of gradients from g0 to gk is linearly independent as well. Okay, these are k plus 1 linearly independent vectors belonging to the span of these vectors, g0, ag0 up to akg0, but the dimensions of this subspace is at most k plus 1, and that's the reason why indeed these subspaces are equal. So g0 up to gk is linearly independent. But that means that k a g0 is the span, indeed the span a g0 a k, that was k g0. Okay, and indeed the dimension here is k plus 1, so I should here write subscript with k plus 1 that I have done wrong here. Here, this is k plus 1. Okay. So it's still left to prove the third assumption, that was, that indeed our directions, which are defined as here above, are conjugate for all components I and j, not only that that one direction is conjugate with the previous direction. So let I be less than j minus 1, since we already know here from the slide that in the case that I is equal to j minus 1, the directions dj and di are indeed conjugate. Then we have di and dj in our energy scalar product. This is nothing but minus di and gj a. This is again by induction, since we know that we rewrite dj as minus gj plus beta k dj minus 1. Okay? And by induction, we know that all directions up to a component j minus 1 are conjugate indeed. So since d0 up to dj minus 1 are conjugate. But for all I plus 1 less than j, it's the same assumption than here, a di belong to the span of d0 up to di plus 1. Okay, this is, due to the fact that di belong to the span up to di, of course. Applying this matrix I, we are in this space, and we have to extend it with one conjugate direction. And therefore, this equals to 0, since the jth gradient is indeed orthogonal with respect to the span of these, there is I plus 1, again, by lemma 5.5 point star. Yeah, we have shown that for general conjugate methods here above, the gradient is orthogonal with respect to the all previous directions, searching directions. Okay? So, now it still remains to prove the fourth assertion. That is just the result that we can rewrite our scalars alpha k and beta k here as follows. Alpha k is defined as minus g k t dk divided by dk transpose a dk. Well, but this is nothing as gk transpose gk divided by dk transpose a dk, and that is exactly what we wanted to show. And why does this hold? Well, this is because of the fact that dk is defined above here in the slide above as minus gk plus beta k minus 1 dk minus 1. And, well, this is the guy, so this term is the remaining term with respect to the first term here of the definition of dk. So the assertion is that gk transpose times dk minus 1 vanishes, but again, this is this formula lemma 5.2.2 star, that these both are that the scalar product of gk and dk minus 1 is 0. So, moreover, we have with gk plus 1 transpose gk that these are equal to 0. And why these are equal to 0, that's the case. We rewrite gk. We rewrite gk by this definition here above as gk is nothing but minus dk plus beta k d. Maybe I write it here down. So gk is nothing but minus d, or is it right? Minus dk plus beta k minus 1 dk minus 1. And again, by our formula star, gk plus 1 transpose dk is equals to 0, and gk1 transpose dk minus 1 equals again to 0. So due to this, we have that beta k is gk plus 1 transpose a dk divided by dk transpose a dk. This is the definition here above. But this is nothing as now we extend this guy with our scalar alpha k. So this is nothing but gk plus 1 transpose alpha k a dk, but alpha k is, well, is this here. So here below we have gk transpose gk. Okay, that's not so bad. Here we have the same written than here. We only have to verify that this guy is the same than this. Well, once again, we use just the definition of our iterates. Here we see in the very first line, this is nothing. So this guy here is nothing but xk plus 1 minus xk. And this guy here, we already have applied it at least twice. Here once and here above once, it's nothing but the difference of our gradients. So we have, this is gk plus 1 a times, not a, this a vanishes, gk plus 1 minus gk divided by this here, gk transpose gk. Okay, and now, due to the fact that this scalar product is 0, this second guy here vanishes, and we indeed have our beta k in that form. Okay, some questions so far? So that was really technical and not that nice maybe to follow, but the next result is really quite nice, I promise you. It's about the convergence rate. And we see here in that result that the convergence rate is indeed better than that of the gradient method or of the Jacobi method, in that meaning that we have, well, the convergence rate of the gradient method is when kappa is the spectral condition number, is where we have it here. The kappa minus 1 divided by kappa plus 1 and the kth exponent. And indeed, in the case of the CG method, we have the square root of kappa minus 1 divided by the square root of kappa plus 1. And kappa, the spectral condition number, is greater or equal, and mostly greater than 1. That means that indeed we improve our method, our convergence rate, in that sense that we improve our kappa of which we have at the convergence rate of the gradient method to the square root of kappa, which is much more less. Okay? And the following, I want to present you the proof here at the blackboard. And the proof is quite nice indeed, because we use this, our subspaces, this Krylov subspace. We have, up to now, we know that our CG method, the kth iterate of the CG method, minimize our functional on the affine subspace x0, that is the initial data, plus this Krylov subspace. But this Krylov subspace consists of somehow, the k-dimensional Krylov subspace consists of all polynomials applied on our matrix A up to the order k minus 1. Applied on this direction G0. And this leads to a very nice proof to obtain this convergence rate. So theorem 5.2.4. Let P be an arbitrary polynomial of order k. Okay, it's not that arbitrary. We have to make some assumptions on our polynomial, as they are a polynomial of order less or equal to k, such that there exists a positive number r, such that for all eigenvalues of our matrix A, so this is set belongs to the spectrum of A, we can estimate this polynomial evaluated on such an eigenvalue by R. And moreover, we want that this polynomial at point 0 equals to 1. Okay? In that case, the kth iterate of our CG method satisfies that the error of the kth iterate can be estimated, the error with respect to the energy norm can be estimated by R times the error we have already done with respect to the energy norm by the choice of the initial data. Okay, we define the following polynomial. This is nothing but the polynomial p minus 1 times z, or more, to be more precise, we divide with z. And this indeed is a polynomial of degree of order k minus 1. Well, why this singularity we do not matter about this singularity. That is why, because of the fact that p at point 0 is equals to 1, so this is indeed just a removable singularity. So the singularity is removable since p evaluated at 0 is 1. So moreover, we said the vector epsilon, the vector y, sorry, is nothing but the initial vector plus a polynomial, this polynomial of degree k minus 1 times G0. Or this is nothing but it's evaluated at with the matrix A. So this is a matrix again. This is applied on this gradient. So we know that this indeed belongs to x0 plus our Krylov space. Okay? And now that is the point that we know that our CG method minimize our functional at exactly this point. So this here is the minima of our functional in this affine subspace. Okay? However, with G0 is, well, it is just the gradient at our initial data of the functional, so it's nothing but this. B is nothing but AX star, when star is the X star is the exact solution. So that leads to y minus X star is nothing but the initial data minus X star plus y minus the initial data. Okay, but this is x0 minus x star, and y is defined as the initial data plus this guy here. Here minus the initial data, this guy remains, plus g a, no, not g, q. qa applied on g0. Well, but what was qa? Qa was this guy here, this polynomial. And we evaluated somehow, we insert this matrix A in this polynomial. But G0 is nothing, where we have it, is nothing but here. The matrix A applied on this guy. So this inverse of A and this matrix A cancel. So this guy here is nothing than P of A minus 1 of x0 minus x star. So this minus 1 times x0 minus x star now cancels with this x0 minus x star. So what indeed remains is nothing but P evaluated at the for the matrix A times x0 minus x star. This is nothing but P A x0 minus x star. Okay, and therefore we have y minus x star. The energy norm can be estimated by, this is equal to this guy here. This is nothing but a matrix again, so it's a linear map. So we can estimate it here by the operator norm of this matrix with respect to the operator norm of generated by the energy norm A times the energy norm of this guy here. Okay, so what remains is somehow to use the minimizing property of our kth iterate and to estimate this operator norm of PA. So estimate this of PA. We have let E1 to En be an orthogonal basis of eigenvectors of A, and we can be sure that such an orthogonal eigenvectors, basis of eigenvectors exists since A is symmetric with respect to the eigenvalues lambda 1 to lambda n for an arbitrary vector W, which then can be represented by a linear combination of these eigenvectors belonging to Rn. We obtain that W, this polynomial of A applied on W can be estimated in the energy norm as follows. So this is nothing but just applying this polynomial of A on that linear combination and applying on each eigenvector Ej. So we obtain such the polynomial at the eigenvalue lambda j. But this can be rewritten as the sum of lambda j, Cj, p lambda j squared. This is due to the definition of our energy norm here, since it is more or less nothing but Ej transpose A Ej. But this is, since Ej is an eigenvector with respect to the eigenvalue lambda j, this is nothing but lambda j and Ej squared, but Ej squared, the absolute value of Ej is 1. Orthonormal, I'm sorry. This should not be only orthogonal, but orthonormal. Okay. So, and now this can be, due to this assumption here we have done on our polynomial, can be estimated by r squared, and here the sum of lambda j Cj squared. And now computing the same steps backwards, we obtain that this is nothing than the energy norm of W. Okay? So we see indeed that we can estimate the operator norm with respect to the energy norm of the matrix PA by this number R we have introduced here. And that means now that y minus x star in the energy norm can be estimated by R, x0 minus x star and the energy norm. And now we just apply the minimizing property to obtain so we have QAG0 belongs to KK AG0. Okay, this is what I already have mentioned. A K minus 1 G0. But XK minimizes also the functional and hence also this energy norm. That means, of course, that x minus x prime A is less than y. Okay, this energy norm, with the k iterate is less or equal than this energy norm with any arbitrary vector y belonging to this affine subspace, and especially in the case when y is defined as here, as we have done here. So, and we are finished. Okay? So, and now to obtain our convergence rate, the challenge is to find suitable polynomials that satisfy these assumptions we have done here in this theorem. For this, we look at the following functions. We consider for any natural number and any real scalar the function tk of x defined as 1/2 x plus the square root of x squared minus 1 plus x minus the square root of x squared minus 1 with exponent k here and here. So then the assertions are that 1 tk is indeed a real valued polynomial of order less or equal to k. The absolute value of this function can be estimated by 1 in the case that x, the absolute value of x, is not larger than 1. The third is that k x is greater than 1/2 and x plus the square root of x squared minus 1k for x larger than 1. And the fourth assertion is that tk at point 1 is 1. This is true, this is 0, this is 0, this is 1, 1 is 2, is 1/2 is 1. Okay. So now let us verify these 4 assertions. The first is the most surprising maybe of these 4, but indeed by the binomial theorem we see that if this discriminant below the square root is negative, then either this exponent by the binomial theorem is even, so it doesn't matter, or it is odd, and in the odd case, this guy and this guy cancels. So indeed, by the binomial theorem, terms square root x squared minus 1 with some power j with odd power j cancel. So the second is that indeed we can estimate it here with 1. We take the absolute value here. By the triangle inequality, we obtain that the absolute value is less than 1/2. And in the case that x, the absolute value of x is indeed less than 1, the discriminant under the square root is negative. That means that we have here a real number, here an imaginary number. And the absolute value of that complex number is then, of course, nothing but the absolute value of this complex number, 1 minus. Okay, now the square root here is a real number, since 1 is greater than x squared, plus x minus I minus x squared k. But these both complex numbers belong to this unit ball. When this the imaginary axis, this is the real axis. This unit ball, yes, since 1 minus x squared is somehow the conjugate of x squared for that unit ball. And therefore, the absolute value here is 1, the absolute value here is 1. We have 2 inside the brackets, 1/2 before, in front, so this is 1. Okay? So the third and the fourth are quite trivial, since in that case that, okay, this is only to just verify it, and in the case that x is greater than 1, these are real numbers indeed, and of course we can estimate this function by omit this second guy here. Maybe you already have seen such functions of this type. We can rewrite it in the case of the argument is less, the absolute value of the argument is less than 1, as follows. This is nothing but the cosinus of k, arc cosinus of x for, maybe in the some numeric lecture you already have seen them. These are the Chebyshev polynomials, which you, okay, I see some of you know that, are called the Chebyshev polynomials, and they find polynomials. For example, they will find application in the polynomial interpolation. Because they somehow optimize the error which are done by polynomial interpolation. Well, now we are almost finished. So we write down our convergence rate we want to prove. And of course, these Chebyshev polynomials are the polynomials we apply this theorem to obtain our convergence rate. So the convergence rate, to write it down once again, now is the square root of kappa minus 1 divided by the square root of kappa plus 1 with the exponent k, x0 minus x star, the energy norm. Okay? So, and this kappa is the spectral condition number. That is nothing but the largest eigenvalue of A divided by the smallest eigenvalue. So, and we call them the smallest eigenvalue A and the largest eigenvalue B. B the smallest or largest eigenvalue of A, respectively. Then I need one more blackboard. So the next time, next week, the last lecture in this year, Professor Knabner will say some words about preconditioner. That are matrices you apply on your linear system to reduce your spectral condition number here. Then, because you see that your convergence rate here is the better the condition. The spectral condition number kappa here is very close to 1. But in often cases, this number is a quite large number. So it makes sense to reduce the spectral condition number by such a matrix applied on the system. And these matrices are called the preconditioner. However, we are, A, B are the smallest and the largest eigenvalues of A, and we set now Px as this Chebyshev polynomial at the point P plus A minus 2x divided by B minus A divided by Tk B plus A divided by B minus A. Okay? We can be sure that we can divide by this function value due to the fact that B plus A divided by B minus A is larger than 1, and in that case we can assume our Chebyshev function here as follows. That means that it does not vanish. But with respect to x, this is just a constant, so this is indeed a polynomial of order k. So, and furthermore, in the case that we have 0, then here these both terms are equal, so that we indeed have that our polynomial evaluated at 0 is 1. And for each eigenvalue, lambda, in the spectrum of A, we can estimate this polynomial evaluated at this eigenvalue by 1 over tk b plus a divided by b minus a. And this guy here is exactly this. Oh, this is of the previous theorem, this positive number r, where which we can estimate our error we made in the energy norm. Well, why does this hold? Okay, this hold since in that case, or in general, this is nothing but this argument is nothing but 1 minus 2x minus a divided by b minus a. And now lambda belongs in between a and b, since a is the smallest and b is the largest eigenvalue. So this argument here is indeed less than 1. And then here we can apply here the second assertion and estimate here this guy here above by 1. So, and now our theorem, which is now no more written at the blackboard, says that we can estimate the error in the energy norm of the kth iterate by, this is smaller than 1 over tk b plus a b minus a times the error of the initial data. Okay? And now it's still left to verify that this guy here, 1 over tk, is nothing but, or can be estimated by this guy of the, depending on the spectral condition number. But, of course, b plus 1 divided by b minus 1, the argument here, is nothing but we divide or we cancel a, so we have here b over a plus 1, but this is nothing but the spectral condition number, plus 1 divided by kappa minus 1. And furthermore, we have tk kappa plus 1 divided by kappa minus 1 can be estimated, since this is, of course, the argument is greater than 1. You can estimate this from below by this 1/2. And this x plus, and this is kappa plus 1 divided by kappa minus 1 plus the square root of kappa plus 1 divided by kappa minus 1 squared minus 1 with exponent k. And finally, we rewrite this guy here. Oh no, we rewrite the complete guy here in the with and the brackets. This here is nothing but, well, it's something like kappa plus 1 plus the square root of 4 kappa divided by kappa minus 1. And this is nothing but, of course, this is nothing but the square root of kappa plus 1 squared divided by the square root of kappa plus 1 and the square root of kappa minus 1. And this is now indeed the square root of kappa plus 1 divided by the square root of minus 1. Okay? And this is exactly what we have done, what we have asserted here in our theorem. So the assertion holds indeed, and we're finished. Okay. Just want to give you an overview how does the algorithm looks like. It looks like follows. You choose an arbitrary initial data, x0, and then you you get your first conjugate direction, that is nothing but minus the gradient of your system. After that, you determine the alpha k to compute the next iterate, xk plus 1. Then you determine the next gradient and the beta k to determine the next conjugate direction, and so on and so on. And either you end after several steps when you have the exact solution, or you end with by this convergence rate when your approximative solution is good enough in your opinion. Okay? So then we are finished for today.